Well, that's a little bit messy. We're doing some example sigma calculations. Sigma. So this guy here, look, you make it like this. It has a little bit of a hat, kind of like a cap. You might find it like an English hunting cap or something, I don't know. Flat on top, and then roll around and come back up and join it at just about a right angle. It looks a little bit like a 6 that's been laid over a little bit. You can think of it that way too. It's the letter S, though. It's a Greek letter S. So it's a small case of the uppercase sigma, which is the one we use for summing, like that. Both of those are sigmas. Lowercase sigma is this curly one. The uppercase sigma is the big E, called sigma. Sigma's not hard to say. And then over here, this mu, which is the Greek M, you make like a long tail and then a little loop like this afterwards. So sometimes the tail's not very long, but it's a little longer on this side than on that side. It looks like a U with something hanging down in front of it, but it's really an M. So you see how it looks like an M and a U. Think of it as an M. M for mean, so mu for mean. And then the way you pronounce the letter is mu, like a cat would make a sound, mu, or how we think cats make sounds. They don't make exactly a mu, but we write it as mu. So mu and sigma, don't say moo like a cow, because it's not moo, it's mu like a cat. Haha, okay. So we want to compute some sigmas. The formula for sigma is the square root of the sum possible values minus mu times their probabilities. Oh, you square that, times their probability. So here, the mu is 1.5. The values are here. So you get 0 minus 1.5 squared times its probability. There it is. 1 minus 1.5 squared times its probability. 2 minus 1.5 squared times the probability of 2. And 3 minus 1.5 squared times the probability of 3. And then I was going to whip out my calculator, but I got stubborn. I said, well, okay, wait a second. This is 1.5 squared, that's 2.25. I know that. We'll just factor out the 1/8. This is a half squared, so it's really 1/4. So this is 3/4 times 1/8. So that's 0.75 times 1/8. And so is this one. And here we go, the same thing as the first one. Okay, we get these. And then coincidentally, or by sheer luck, that's 3, so it's 6/8, which is 3/4. Take the square root, you can find 866. I needed the calculator for the square root. And here's the coin toss, 1 for heads, 0 for tails. The distribution of that random variable looks like this. The mean, mu, oh there it is, was 1/2. So we'll have 0 minus 1/2 squared and 1 minus 1/2 squared times the probabilities. And we take the square root. So squaring 1/2 gives you 1/4 times 1/2 gives you 1/8. Happens here too. So you get 1/8 plus 1/8, that's 1/4, and then you take the square root, you get 1/2. So we survived those calculations without a lot of pain. And that, as you might think, or you might wish it hadn't happened, there's the formula that makes sense conceptually, and there's a formula that makes sense computationally, which might avoid some rounding. So here is the computational formula for the standard deviation of a discrete random variable. It's the square root, and here is x squared times p of x summed together, and then minus mu squared. So we can compute x squared times p of x. We square each of these and multiply them by this number. So 0 squared times that, 1 squared times that, 2 squared times that, 3 squared. So it's 0 times 1/8, 1 times 3/8, 4, which is 2 squared times 3/8, and 9, which is 3 squared times 1/8. We add them up. 0, 3/8, 12/8, and 9/8. 3 plus 9 is 12, and 12 more, that's 24/8, which is 3. And then we get mu squared, which is 1.5 squared, which is 2.25. Put 3 here, put 2.25 there, there they are. I should write sigma here. Sigma equals, and that's the square root of 3/4, that's what that was, so we get 866. So that's a lot of computing for not a lot of results. And that ends our small foray into just general conditions and procedures you might follow to analyze discrete random variables. And I'm closing off this section like this.